Ever notice how AI sometimes delivers flawless answers, while other times it sounds like it's making things up? That's not just random. It's a complex interplay of how models process information. Today, we're diving into the science behind AI hallucinations, the breakthroughs in making models self-aware, and how researchers are training machines to learn from their own mistakes. Let's get technical. So here's the core issue. Large language models don't understand the information they process. They're like students who have memorized textbook answers, but can't explain the underlying principles. When they generate text, they're essentially pattern matching based on statistical probabilities. If the data they're trained on has gaps or ambiguities, they'll fill in the blanks with plausible sounding but incorrect information. This is what we call a hallucination, a fabricated response that sounds authoritative but lacks factual grounding. The problem is that most models lack a built-in mechanism to detect these errors. They don't have a truth checker like humans do. Instead, they rely on external feedback to correct themselves. Think of it like a student solving math problems without a teacher. They might get the right answer, but if they don't understand the process, they'll repeat the same mistakes. This is where researchers are focusing their efforts, teaching models to recognize when they're wrong and adjust accordingly. Here's where things get interesting. Traditional AI training involves brute force memorization of examples. It's like teaching a child to solve equations by drilling them with problems until they can recite the solutions. But a new approach called in-context learning is changing the game. Instead of forcing models to memorize, researchers are showing them how to solve problems by providing curated examples. It's like giving a student a set of step-by-step guides tailored to their learning style. The key innovation here is how examples are selected. Early experiments revealed that models perform better when they're exposed to the most informative examples. Think of it as a museum of knowledge, where only the most relevant artifacts are displayed. Some teams are even using adaptive techniques, where the model itself identifies which examples to prioritize based on its current understanding. It's like personalized tutoring for machines, where the AI dynamically adjusts its learning strategy. The results are striking. When models receive high-quality, contextually relevant examples, their accuracy improves dramatically. For instance, in tasks requiring logical reasoning, models trained with curated examples outperformed baseline systems by over 40%. But there's a catch. Too many examples overwhelm the model, while too few leave it underprepared. It's a delicate balance, like training a dog with just the right amount of treats to reinforce the desired behavior. Of course, this isn't a silver bullet. Even with these advances, models still struggle with deep conceptual understanding. They excel at pattern recognition, but lack the ability to reason abstractly. That's where frameworks like Mockingbird come in. This approach doesn't just teach models to memorize solutions, it trains them to think like problem solvers. By integrating self-reflection mechanisms, Mockingbird allows models to evaluate their own reasoning and adjust their outputs in real time. Let's break down how Mockingbird works. Imagine you're solving a complex puzzle, and every time you make a mistake, you jot down a note about what went wrong. Later, you review those notes to avoid repeating the same errors. Mockingbird does something similar. When an AI explores a problem, a branch of reasoning, it records its steps and outcomes. If it fails, it compresses those errors into a concise summary, a kind of cheat sheet for future decisions. This prevents the model from tripping over the same potholes again. The results? Phenomenal. In one test, an AI's accuracy in classifying poisonous mushrooms jumped from 37% to nearly 90% by following a simple substitution script, a set of rules generated by the model itself. But there's a caveat: these scripts work best for structured tasks. When faced with messy, real-world data like predicting car prices, the model's logic often breaks down. That's why tools like Mockingbird let users toggle between rigid rule-based systems and more flexible, dynamic approaches. So what's next? As researchers refine these techniques, we're inching closer to AI that's not just smart, but self-aware, able to learn from its mistakes and adapt to new challenges without constant human intervention. It's a paradigm shift in how we train machines, and the implications are huge. Want to see how this works in practice? We'll walk through the code and experiments in our next video. Thanks for watching. Drop a comment below. What AI challenge do you think deserves the most attention? Let's keep the conversation going.